Okay, now we're going to continue, and the next subject that I want to speak about is called reaction mechanisms. There are too many things here. Reaction mechanisms. Now, reaction mechanisms in organic chemistry it's like this fiction that you can see. You can describe a slow motion movie of what happens when a reaction takes place. I shall give you, of course, some examples, but let's just keep that in mind, that a reaction mechanism is a description of the kind of dance of atoms that happens when a chemical reaction happens. A slow motion movie of the molecular events that take place when an organic compound or a set of compounds undergo chemical changes. So here's an example. I'm going to represent cyclohexanol. I don't want that. OH is in the presence of an acid. So in the first step of the mechanism, the hydroxyl group is protonated. It receives a proton. So we have OH. Now that protonated OH group has a charge. If in the second step, after protonation of the alcohol, the water is lost. If the water is lost, now this is an important thing. In fact, I shall use a different color. If the pair of electrons that presently holds the hydroxyl group to the carbon, if that pair of electrons leaves with the water, that's the importance of that curved arrow. I will emphasize this again and again because it's a very useful thing to understand. If that curved arrow is realized, the carbon that had anchored the protonated water, protonated hydroxyl, now has a positive charge. So I'm representing in that little circle a positive charge on the carbon. Now, I shall teach you a word, but we'll get it many more times. Carbocation. A carbon that bears a positive charge is called a carbocation. It is an example of a reactive intermediate. This is also, let me finish writing. It's also an important and useful notion that there are certain chemical species which don't last very long. They are intermediates and they're very unstable and they're going to do something quickly. That's an example of one. Now, if in the presence of any chemical species, represent the carbocation, in the presence of any chemical species that has a pair of electrons available for forming a bond to a carbon, as for example, if I had a bromide anion, it would find that carbocation irresistible. And again, using the curved arrow notation, the bromide would attack that carbon and share its pair of electrons. So in the result here, the entirety of the reaction is shown as a bond between a carbon and a bromine. These three steps constitute a mechanism for the substitution of a hydroxyl group by a bromine. Cyclohexanol becomes cyclohexylbromide. My next subject is called bond cleavage, meaning how do bonds break. If A is bonded to B, there are a couple ways that that bond can break. And I shall use, and I want you to get used to this because it's useful, a curve down notation. If what is represented by that red curved arrow is that a pair of electrons which had been held commonly between A and B, if the pair of electrons splits and leaves with a B, the product of that, product implied by that curved arrow is that A is left missing an electron and B leaves with an electron. This is an example of what's called heterolytic. One chemical species gets the electrons that used to be shared, and one chemical species is left with none. There is another mechanism, let me write under this one. This one is heterolytic. Now consider the following. Now I'm going to introduce a new symbol. I'm going to describe a curved arrow. I'm going to draw a curved arrow which only has one barb on it. In this case, if curved arrow with just one hook on it, if the pair of electrons that share between A and B one electron leaves with A and one electron leaves with B, the split of the bond is homolytic. Both A and B get an electron. So we, in this case, we would have A with an electron plus B with an electron. This is called a homolytic cleavage. It's almost self-evident, but I will point out that it's important in this business. It's not hard, but it's terms that I would like you to understand and not let go of. A heterolytic cleavage produces ionic species. A homolytic cleavage produces what are called, and again, this is another new word, these are radicals. There are two here, an A radical and a B radical. Any chemical species that has an unpaired electron is called a radical. It's an unusual use of the word, but it's in this business of chemistry, it's a real word, and every chemist in the world knows what that means. It means chemical species that has an unpaired electron. If the shared pair is homolytically split, each of the parties formerly bonded to each other leaves with an unpaired electron. Now, it turns out that radicals are a second kind of reactive intermediate. Earlier on, in the last little board that I had, I showed you a carbocation. In this case, we're looking at radicals as another chemical and intermediate. It doesn't hang around for long because it's very unstable and it'll do something.